Howdy! This is your friendly neighborhood physics teacher here, and we're going to talk about the last unit of the fall final review. This is Unit 4, and this is the force unit. Now, just like the other ones, if you haven't answered these questions, stop the video. Answering the questions before looking at this video is highly suggested. Because, yes, you'll be able to do it because I'm sitting there explaining it to you. There's a difference between you doing it by yourself and then going back and checking, oh, yep, I did it right, or, oh, there's where I went wrong, versus, oh, I get it, when you're sitting here watching me do it. So stop the video, do it yourself, and then come back and watch the video. It's okay. For the ones that have done the questions, let's continue on. We're going to scroll up to the very top of our review because we have a few more the variables that we have not done. So we're going to do the variables that deals with the force unit. And actually that starts with, we've already done acceleration due to gravity. And so we do deal with acceleration due to gravity and acceleration, but we did those on the previous units. So we're going to start at force. So force, its variable is represented with an F, capital F. It's measured in newtons, and it is a vector. Next one is frictional force. That is represented with a capital F with a sub F, frictional force. It's measured in newtons, and it's a vector. All forces are a vector. All forces are measured in newtons. So we're going to get lots of repeats here. Force on normal is represented with an F with a sub letter N. You could do capital or lowercase, whatever floats your boat, with, again, measured in newtons, and it is a vector. We have force of gravity. Force of gravity is represented with a subletter G there, again, measured in newtons, and it is a vector. We have force of gravity in the y direction. Force of gravity is F sub G with a sub y, still measured in newtons, and it's still a vector. Force of gravity in the x direction, so it's Fg sub x, newtons vector. You can just, anytime you see force, just ditto. Force applied, guess what? Fa, so F sub a, newtons vector. We have force applied in the x and force applied in the y, so it looks just like the force applied, force of gravity, just F of y, Newton vector, F of a x, Newton vector. And then we have universal gravitational constant. So that is represented with a big G, and that is a constant. So that is 6.67 times 10 to the negative 11. And your units for that are meters squared. Newtons. That's what I was forgetting. I was like, I'm forgetting something. Newtons times meters squared divided by kilograms squared. And that is a constant. And that isn't a vector. That is a scalar. That number is a scalar, but it's just a constant. Scalar. There we go. I believe that is it. We filled out the whole entire variable, unit, constant, vector, scalar little thing at the beginning. So now we're going to scroll down to Unit 4. That should be near the beginning of page 6 of your review. And we're just going to start with question 1. Question 1 states, what happens when all forces on an object are balanced? All forces on an object are balanced. So we're going to draw our object. We have a force going to the right, force going to the left, force going up, force going down. So the force going up is 10, the force going down has to be 10. The force going to the right is 5, the force going to the left has to be 5. So your forces are balanced. If you notice, you have 10 going up and down and 5 going left and right. Those up and down, left and right don't have to be balanced because the ones going left and right only deal with the ones going left and right. The ones going up and down only deal with the ones going up and down. So those don't have to be the same number. Just in the x direction and the y direction have to be in the same number. So the ones in blue are y, the ones in purple are x. Those have to be balanced. This object could be doing two things. this object could be doing two things. It could be doing A, resting. That means it's not moving at all, so it makes sense that there's no acceleration. Or it could be moving at constant velocity. Or it could be moving at constant velocity. So those are the two things this object could be doing since it's balanced. We don't know which one unless we have some other reference. But if you see a balanced object, you know it's either A, resting, or B, moving at constant velocity. That reason is because your acceleration equals 0. In both of those cases, your acceleration equals 0. A, object not moving, so of course there's no acceleration. Or B, constant velocity. Constant velocity means your velocity is not changing. The whole definition of acceleration is the change in velocity. So we don't have any change, we can't have any acceleration. Next question. What happens when the forces on an object are not balanced? So we're going to have this little box here. And again, we'll keep it sitting on the ground. So going up and going down will still be 10. But now we're pulling it 15 to the right. And friction's only affecting it by 5. So now the object is not balanced. It is accelerating. So there's only one thing could be happening when it's not balanced. It's accelerating. Accelerating. It means the box is moving, and it's moving in a speeding up or slowing down fashion. In this case, it's speeding up because we're pulling it to the right. It's overpowering the friction, so it is moving. If it was like other way around, it could just be moving to the left, just in the negative direction. Left is a negative direction, and anything like that. So it is accelerating. It's either accelerating in the positive or negative fashion. So question 3, what are all the forces we label on a free body diagram? So forces we can label. First one, hopefully, that pops in your head is force of gravity. And which direction does force of gravity goes? It goes straight down. The next one is force of normal. Force of normal goes with the surface. So in this case, the surface, it's flat, so the force of normal does go straight up. But let's say our surface is tilted. Our force of normal tilts with the surface. Our force of normal tilts with the surface. It doesn't matter which direction it's tilting. It tilts with the surface. Force of normal can even be, if you're leaning up on a wall, your force of normal can even be straight off the wall. It goes with the surface. Next one would be a force of friction. Force of friction always goes opposite of the motion. So if we have a brick and it's being dragged that direction, that means, so this is motion. That means your force of friction goes opposite of the motion. Same thing if you have a brick and it's falling, because of force of gravity, it's going down, the motion is down. That means you have some force of friction going up. Force of friction is opposite of the motion. Force of friction is opposite of the motion. Now we have a force applied. And force applied could be anything that you're pulling, pushing, anything. Force applied can go in any direction that you're doing. It could go that way. It could go at a diagonal. It could be you're pushing it down. Force applied can go in any direction, just according which direction you're pulling, pushing, shoving the object you're trying to do. So force applied can go in any direction. So you have to actually read the situation to know exactly which direction that force applied is going. So that's our main forces. You have force of gravity, force of normal, force of friction, and force applied. Now your force applied and your force of gravity could be broken down into its x and y components if it needs to be. So you can have force applied in the x, you can have force applied in the y, you can have force of gravity in the x, and you can have force of gravity in the y. But you only need to do that if those forces are at an angle. So you only need to do that if these forces are at an angle. Okay? You only need to do that if those forces are at an angle. Number 4. What's the 3 laws of Newton? So the first one is pretty much the law of inertia. And basically what that says is an object in motion stays in motion, an object rest stays in rest, unless it's acted upon an outside force. And also, the greater the mass, the greater the inertia. So if you have a big mass, you have big inertia. If you have a little mass, you have little inertia. It's easier to stop a pebble than it is a boulder type of thing. And it's because an object in motion wants to stay in motion. That boulder wants to keep going. Even if it rolls over you, that boulder wants to keep going. The second law is just your equation. Your force equals your mass times acceleration. That's just your equation. Force equals mass times acceleration. The third law is your action-reaction. So for every action, there's an equal and opposite reaction. So it's your action-reaction. Action-reaction. So if I push on the table pushes back up on me. If I push the wall pushes back up on me. If the book is pushing the table is pushing back on the book. It's that aspect. If a gun fires, the bullet goes forward, the gun goes backwards because action-reaction. The gun's pushing on the bullet's pushing back on the gun. If I'm sitting in a rolly chair and I throw a ball, I'm pushing the ball's pushing back up on me. So as long as there's no friction, we're both going to end up moving. The reason you don't necessarily see that in real life is because we live in a friction world. So the friction causes the person from moving. But if we were in a frictionless world, you can actually throw the ball and the person would be moving back. It's really fun if you have an opportunity to ice skate at any point in time during this winter. Go up to a friend and push off the friend. Y'all both move because you're pushing on them, they're pushing on you, action-reaction. So it's kind of cool. So those are the 3 main laws. And yeah. So number 5, it says if a 20,000 Newton car is accelerated at 2 meters per second squared, what is the force acting on the car? It's a weirdly questioned thing. So we have a 20,000 Newton. So that is, when it does like that, that's talking about the force of gravity. So that's the force of gravity of the car. And it says it's accelerating. The car is accelerating at 2 meters per second. And it's wanting to know the force so it's pretty much wanting to know your force applied. It's wanting to know your force applied. So these are your givens. Here's your unknown. So what equation are we going to use? The main equation we have is F equals ma. So any force can equal your mass times acceleration. Well, we have our acceleration. We're looking for our force, but we need our mass. Is there a way that we can solve for mass? Well, remember, and I believe it's step 2 on any of our problems, you can solve for your force of gravity or your mass. Because force of gravity equals mass times acceleration due to gravity. So acceleration due to gravity becomes a constant also. It is 9.8 meters per second squared. So if we know our force of gravity, 20,000, we don't know our mass, that's what we're looking for. We have acceleration due to gravity. To get mass by itself, you just divide. What you do to one side, you gotta do to the other. And so the mass of the car ends up being, after you plug that into your handy dandy calculator, and make sure you put enough zeros. Enough zeros. You get 2,040.82 kilograms. And that is now your mass. And so you're able to find your force applied because you take your 20 440.82 times your acceleration, which was 2. You just plug that into your handy-dandy calculator, and you get that your force applied equals 4,081.63 newtons. So this was a two-step problem. You had to find the object's mass. You can do that by using your force of gravity. You can find your object's mass anytime you have force of gravity, because you know the acceleration on Earth is just 9.8, and then you had to multiply that by your acceleration. So that was number 5. So how do you calculate force of gravity? We just kind of talked about that in the last one, but your force of gravity equals your mass times your acceleration of gravity. And as long as you're on Earth, your acceleration due to gravity is going to be 9.8 meters per second squared. Now, if you're on the moon, your acceleration on the moon is going to be 1.62 meters per second squared. And of course, you change another place, that'll be different. So it's constant for that planet. So you want to double check and make sure you know what planet you are in. If the problem doesn't state you're on a different planet, it is safe to assume that we're talking about Earth. But just make sure that if we're talking about different planets, you double check the acceleration due to gravity on that planet. And it also says, how do you calculate weight? So weight is the exact same thing as force of gravity. Weight, force of gravity is the same thing. Weight and force of gravity is the same thing. So when you step on a scale and it gives you your weight, that is your force of gravity. It's just in pounds versus newtons. That's it. It's the same thing. You can convert pounds to newtons. But just like how we convert inches to meters, it's just a conversion. But weight and force of gravity are the same thing. The next question is, how is weight different from mass? And that's one thing. When y'all were doing these bridges, y'all kept saying, what's the weight of my bridge? Like, unless you're multiplying that number by 9.8, that is giving you the mass. You mass your bridge. You don't weigh the bridge with the scale that we're using. So it's two different things. Weight is a force. Weight is a force. Go away. There we go. Weight is a force. So you actually have to do some math to get it. Weight changes from planet to planet. Weight changes from planet to planet. Now, your mass is how much material or how much matter it is used to make you or to make that object. When you have you and then you step on the moon, does your matter change? No, unless you've lost an arm and a leg from here to there, your matter does not change. So mass does not change. Weight is a force. Mass is how much matter is used to make you. So, I did that horrible joke in class. It shouldn't be called Weight Watchers. It should be called Mass Watchers. Because the only really way to change your weight would be to go from planet to planet. When you physically gain or lose weight, you're physically adding or losing mass. That's your fat cells or muscle. So you're gaining muscle or you're gaining fat, or losing muscle or losing fat. You're gaining or losing matter to change your weight, because weight is a force, so it's your mass times your acceleration. It's mass times your acceleration. Mass is just mass. Please get that. There will be a test question on that. Please, 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 please get it. Thank you. Does the mass depend on the acceleration due to gravity? Does the mass depend on the acceleration due to gravity? The answer is no. It does not. Because remember, the mass is how much matter. Now, your weight does. Your weight depends because your weight is a force. Force is mass times acceleration. Your weight depends on acceleration due to gravity. Your mass does not. Does the weight depend on the acceleration due to gravity? That one's yes. So the no goes with question 9. The yes goes with question 10. It's because it goes back to your weight being a force. So it goes back to your weight being a force. 11. What is the normal force acting on a 20 kilogram box that is being pulled forward with 10 newtons? So we have a box, and the mass of the box is 20 kilograms, and is being pulled forward with 10 newtons. So forward at 10 newtons. So that would be the force applied. Force of gravity goes straight down. You have a force of friction. Remember, force of normal goes with the surface. It's just a flat surface, so it's there. So is the box moving in the y direction? So is the box moving in the y direction? Hopefully you said no. Not moving. Because we know it's moving in the x direction. Because it's being pulled in that way. Oh, jeez, it jumped around. Moving. So the way to find normal force would be you have to find your force of gravity. Your force of gravity equation equals mass times acceleration due to gravity. We have the mass, 20. We know the acceleration to gravity on Earth is 9.8, so you just have to plug that into your calculator. You just do 20 times 9.8. So your force of gravity is 196.0. So that is your force of gravity. So therefore, since it's not moving, it's balanced. Your force of normal also equals 196. Now that only works if it's A, on a flat surface, and B, it's not moving in the y direction. So number 12. A 0.011 kilogram racing snail accelerates from rest to 10.8 meters per second in 0.030 meters. What is the net force on the snail during this period? So we're looking for net force. Let's do our givens. So our givens. We're given mass. Mass is this horrible number, really small number, because we're dealing with a snail. And it says from rest. Rest is a given also. So from rest, that's telling you your initial velocity is 0. And it's saying that it goes to 10.8, so that's your final velocity. And it does, and it does that in, so that's your meters, so 0.03 meters. And it's looking for net force. So our unknown is net force. Another way to write net force is the sum of the forces. So that's another. So you're looking for, that's the same thing. That is the same thing. So we know our equation for net force. Our equation for net force is mass times acceleration. Well, we have the mass. We have the mass, but we don't have acceleration. Could we use what we have to solve for acceleration? Well, we have initial, we have final, and we have x. So guess what? We got to dive into that 1D motion. It's not over. It all connects. So we have our final velocity squared equals initial velocity squared plus 2a delta x. So we can actually find our acceleration. So final velocity was 10.8 squared. Initial velocity was 0. We're looking for acceleration, and our displacement was that. So 10.8 squared, we get a really big number. Not a really big, just a big number. 0 squared just gives you 0. 0 plus a number just kind of goes away. You can go ahead and do 2 times 0.03 and get 0.06 a. We want a by itself, so we got to divide what we do to one side. We got to do to the other. So we get that our acceleration, man, that snail's booking it, 1,944. That's our acceleration, meters per second squared. So now we can just go over here, plug that into our acceleration. We have the mass. The mass is a small number, right? Yep. Our mass is a small number. And now we have the acceleration that we solved for. You just multiply that by the mass. And you get the net force acting on that little tiny snail be 21.38 newtons. So yes, so we connected 1D motion with forces. You can do that, and we did on the test, so I would know to make sure I know how to do that. So 13, if a child pulls a 20 Newton box east on a box, and a child pulls 18 newtons north on a box, what is the net force on the box? Remember, force is a vector. You need to have magnitude and direction in your answer. So let's kind of draw it out. When in doubt, draw it out. So one kid is pulling on a box, and it's going 20 newtons east. The other one is going 18 newtons north. So 18 newtons north. Which direction is this box going? So remember, all the forces in the y direction only interact with forces in the y. All the forces in the x direction only interact with forces in the x. Lucky for us, we don't have any forces going south or west. So now we just make a triangle. So we know it's going 20 east and 18 north. Notice how I drew my vectors. Because you have to draw the one going x first, and then the one going to the y. And so you have your hypotenuse is going in the right direction. So it makes sense that this box is going at a diagonal to the northeast. If you drew it the other way, if you drew it like this, your box would be either going northwest or southeast. But you know the box isn't going in that direction. So that is wrong. We do not do it in that fashion. So you have to make sure you draw your vector from tail to head, and then you start back where you're going and go. And to find your hypotenuse, you just use Pythagorean theorem. So you do a squared plus b squared equals c squared. It doesn't matter which one you make, a or b, so you can just do 20 squared plus 18 squared equals c squared. 20 squared gives you 400. 18 squared gives you 324. You just add those two up, and it gives you 724. How do you get rid of a squared? Use square root. What you do one side, you got to do to the other. So the square root of your answer is 26.91. So that is your hypotenuse. That is your magnitude. So that box is being pulled 26.91 in this direction. Now it says for direction also. So that's how much. Direction, when it says direction, it's meaning your angle. So it's meaning your angle. So we need to figure out the angle. And this one, since we have all three sides, you can use sine, cosine, or tangent. It doesn't matter which one. I'm just going to use sine. So sine angle equals opposite over hypotenuse. This is your angle. 18 is your opposite. 20 is your adjacent. And 26.91 is your hypotenuse. You plug in what you got. We don't have angle, but we have opposite. 18, your hypotenuse is 26.91. We need theta by itself because that's what we're looking for. To get sine on the other side, you have to do the inverse. 18 divided by 26.91. To get inverse, you hit second sine on your calculator, and you should see a sine -1 parentheses. Then you just do 18 divided by 26.91, and your angle ends up being 41.98 degrees. And that'll be in your first quadrant. Remember about your quadrants. Quadrant 1, 2, 3, 4. Quadrant 1 is from 0 to 90, so you'd be in your first quadrant at 41.98 with a hypotenuse of 26.91. That's also your resultant force. 14. Newton's universal law of gravitation states that the gravitational force between two objects is blank proportional to the product of the mass and blank proportional to the square of the distance between the object. So now we're talking about the fourth law that Newton put together, and it's your universal gravitational law. So we're using the universal gravitational equation. So we're wanting to know the relationship between the force of gravity and mass and the force of gravity and your distance. So remember, you can pull out and just focus in on those two objects. It doesn't matter which mass you use. So if you're looking in, so force of gravity is on top and your mass is on top. So that is a direct relationship. That is a direct relationship. As force of gravity increases, your mass increases. As your mass decreases, your force of gravity decreases. That is a direct relationship. Now for your force of gravity and your distance, they are one's on top, one's on bottom. So that is an inverse relationship. And we can't forget about that squared. Can't forget about that squared. So it's actually an inverse squared relationship. As your distance increases, your force is actually going to decrease. As your radius decreases, your force is actually going to increase. If you think that logically, that makes sense. The closer you get to an object, the more it's going to affect you. The further you get from the object, the less it's going to affect you. The bigger the object is, the more force it's going to have. The smaller the object is, the less force it's going to have. So you can think about these conceptually also, not just mathematically. So in this case, our answer is going to be B. So for 14, your answer is B. 15. If the mass of the moon is doubled and the mass of the Earth remains the same, what happens to the gravitational force between them? It actually doubles also. So it's direct. Mass force is direct. So it'll end up doubling. So 15, the answer is B. 16. If the mass of the moon and the Earth remain the same, but the distance between them two is cut in half, what happens to the gravitational force between them? So as distance decreases, your force increases. But we have to take that squared in consideration. So if it's halved, so that means you would have to take that squared into consideration. So it's 1/4 because 2 squared is 4. So it actually increases by 4. So it would quadruple. So your answer is D. for 16. 17. Compare the magnitude of the force that the Earth exerts on the moon and the force that the moon exerts on the Earth. So this is your action-reaction pairs. Remember, they're the same but opposite. So 17, your answer is A. If you look at your equation, there's only one force of gravity in your equation. There's only one force of gravity in your equation. So therefore, you can only have one force of gravity. So it's the same. Question 18. Find the missing forces for each object. So again, you're trying to see what's happening. So for the first box, it says your net force is 0. So that means your acceleration is 0. So that means everything is balanced. Everything is balanced. So for everything to be balanced, your A would have to be 50 because X's only interact with X's. And B would have to be 200 because, again, Y's only interact with Y's. The next one says your net force is 900. Up. So 900 up. So for C, you can look at it like this. So you know your net force is all your forces added together. So it'd be C plus minus 200. So remember, 200 is minus because it's going down. So you have to take that direction into consideration. So we know the net force. It tells us our net force. Our net force is 900 up, so it makes it positive. So if you need to figure out what C is, just get C by itself. If it's being subtracted, the opposite of subtract is add. So you just do, so you know your C has to be 1100 newtons. D, again, it says your net force is 60 to the left. So you're only worrying about the forces in the X direction. So you're only worrying about the 80 and the D. So it says your net force left is 60, and it's negative because it's going to the left. And that would equal your D plus negative 80 because that's going to the left. So you can figure out what your D is. Opposite of add or subtract is add. What you do to one side, you have to do the other. So that means your D equals 20 newtons. So for it to be moving 60 to the left, that D is slowing it down by 20. E, to figure out E, again, it says it's only going 60 to the left. So that means it's not moving up or down at all. It's balanced up and down. So your net force in the Y direction is 0. So that means they're balanced. So since we have 300 going up, that means we have 300 going down. So your E equals 300. For your next one, it says your net force is 30 to the right. So again, we're just worrying about forces in the X direction. So your net force is going to be G plus negative 20 because it's going to the left. And it says it's 30 to the right. So that 30 is going to be positive. We're looking for G. To get G by itself, the opposite of subtract is add. What you do to one side, you got to do the other. So you get 50 newtons. So your G has to be 50 newtons for it to be going 30 to the right because it's being slowed down by 20 to the left. The next thing is, again, it's moving to the right, so everything going up has to equal everything going down. So therefore, whatever your F is, your H has to be the same. So whatever your F is, H has to be the same. It could be 10, 20, 30, insert number here. Your F has got to equal H. 19. So it wants you to think about Newton's laws here. Why does the last ball move if the first ball is dropped on the second ball? Again, that's an action-reaction pair. So for 18, it's talking about an action-reaction pair. Action-reaction pair. So if you have the calculator that's sitting on your desk right now, the calculator is pushing down on the desk. Well, the desk is pushing back up on the calculator. When the gun's being fired, the gun's pushing on the bullet, the bullet's pushing back on the gun. That's why you have recoil. And again, we talked about, if you're on ice, the reason ice works because it doesn't have very much friction. When you push off of a friend, you're both are going to end up moving because you push off a friend, the friend pushes off on you. If you're in a frictionless world and you're sitting in your chair and it's a rolly chair, you throw a ball, the ball will go flying. Well, so are you, because you're pushing on the ball pushes back up on you. That's an action-reaction pair. 20. Look at the box on the ramp problem. So this is when you're going back to your force test. You're looking at that specific problem. I highly suggest you do that. I also highly suggest you to look at through all the problems. You never know when that problem might reappear, including free response or multiple choice. I'm not kidding, guys. I said this all 4 videos. Look at your multiple choice. I'm actually making the free response very obvious because I'm telling you which ones to go back. I'm telling you, there are multiple, repeats of multiple choice. Look at your old tests. They will and they might have reappeared. So please look at your old test. But right now, we're going to look at the box on a ramp problem. We're going to look at a box on a ramp problem. And you get the formulas. You'll get step by step everything that you had on the box, on the ramp formula that you had on the last test. So I'm pulling up. Sorry, I'm trying to pull up the question. And to make sure I give you the exact same givens, like different types, different numbers, of course, that you'll have on your test. To make sure it's very, 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 very similar. So you have the mass. So we'll give you the mass. The mass of the block will be 17 kilograms. And we'll give you the angle. The angle will be 20 degrees. And we'll give you the coefficient of friction. Remember, that is just your mu. And we'll make that 0.32. Remember, no unit goes with the coefficient of friction. And you're looking for the following. So the first thing it asks you to find is your force of gravity. Now, before you even do that, I highly suggest you to draw your free body diagram so you kind of know what's going on. So your force of gravity, remember, goes straight down. Your force of gravity goes straight down. Then you have your force of normal. It goes with the surface. So since your surface is tilted, your force of normal is tilted. Then you have your force of friction. Remember, force of friction goes opposite of the motion. So your block is trying to go down the ramp, so therefore your friction is going up the ramp because it's trying to keep it on the ramp. Now this one, we have to change our frame of reference, kind of tilt our head. So now with the ramp, this is our x direction, and that is our y direction. So the one that becomes at an angle is your force of gravity. So you draw your force of gravity in the y, you draw your force of gravity in the x, and then your angle, since it's down here, be the same as this angle up there. And that is a 90-degree angle right there. So now we have our free body diagram. Finding our force of gravity, just mass times acceleration due to gravity. We've given you the mass, it's 17. Acceleration due to gravity, we're on Earth, so it's just 9.8. So you just do 17 times 9.8, and you get 166.6 newtons. So that is your force of gravity. Next thing, it asks for your force of gravity in the x and force of gravity in the y. That's when you have to do sine and cosine. So remember, since your angle's up here, this becomes your x becomes your opposite, your y becomes your adjacent, and of course your force of gravity is your hypotenuse. So we can do, for your force of gravity in the x, you would end up doing sine. So sine theta equals opposite over hypotenuse. We know the angle. The angle is 20. Opposite is what we're looking for. It's force of gravity in the x. Adjacent, your hypotenuse, is what we just solved for force of gravity. We need force of gravity in the x by itself. So the opposite of divide is multiply. What you do to one side, you have to do the other. So that ends up canceling. So you end up getting your force of gravity equaling 166.6 times sine of 20. And you just plug that in your calculator. So 166.6 times sine of 20. And you end up getting a 56.98 newtons for your force of gravity in the x. Now, for your force of gravity in the y, you'll end up using cosine. Now, you can use Pythagorean theorem. Since you have both sides, you can use Pythagorean theorem. I just tend to use cosine. So that's adjacent over hypotenuse. You have your angle, which is 20. Adjacent's what we're looking for, so that's your force of gravity in the y. You have your hypotenuse, that's 166.6. Again, we need force of gravity in the y by itself. The opposite of divide is multiply. What you do to one side, you have to do the other. And so you end up getting your force of gravity in the y equaling 166.6 cosine of 20. Plug that into your calculator. And you end up getting 156.55 newtons for your force of gravity in the y. Next thing it asks you is for your force applied in the x. Now that force applied in the x is just what's causing it to go down the ramp. So what force is pointing down the ramp? That is your force of gravity in the x. So your force of gravity in the x also equals your force of gravity, or your force applied in the x. That's what's physically causing it to go down the ramp, is that 56.98. Next thing it asks for is your force normal. In this case, force normal, it doesn't go straight up, it goes off at an angle. So you need to figure out what counteracts that off the angle. Well, your force of gravity in the y. So your force of gravity in the y is the same thing as your force of normal, just opposite but equal, because it's not moving in our new y direction. Next thing it asks you is for your force of friction. So your force of friction equals your mu times normal force. Mu was given. Mu was 0.32. Normal force, it's the same thing as your force of gravity in the y. So it'd be 156.55. And you just plug that into your calculator. And you get your force of friction to be 50.1 newtons. So that's your force of friction. Next thing it asks for is your force net. So remember, your force net, because we're force net in the x direction, because that's the direction it's moving in. It's moving in the x direction. So what force is causing it to go down? So that is your force applied in the x direction. What's trying to keep it from going down? The force of friction. So your force applied in the x is just your force of gravity in the x. So it'd be 56.98 minus your force of friction, which is 50.1. So that is your net force in the x direction. You just do a little bit of math, or you can put it in your calculator, and you get 6.6 6.88 newtons. So that is your net force. That's how much force is going in the x direction. Now, to figure out your acceleration, you know that your net force also equals mass times your acceleration. You know your net force is 6.88. Mass was part of the givens. Where'd it go? And it is 17. So mass is 17. And you're looking for your acceleration. You want A by itself. It's being multiplied. The opposite of multiply is divide. So you end up just doing 6.88 divided by 17. And you end up getting a 0.41 meters per second squared. So that box isn't moving very fast, but it's moving. So that's how you do each part of the problem. Again, we kind of break it down for you. Hopefully that helps. Again, I would advise you to go over all the tests. All the tests but one is in your normal physics folder. If you remember the first test we took, that one is in your academic lab folder, Schoology. So to see that test, you would have to go back there. But hopefully that helps you. All 4 videos are done now. If you have any questions, just let Miss Heath or Miss Verona know. Happy studying. Bye.